go ahead and start our session 3. So I think it works out very nicely with this time zone between Canada and India. It's quite nice to start and end the day with these interesting talks. So thank you to everyone who's joined in and the wonderful speakers we've had so far. So today is, or this evening or this morning, depending on where you are, is session 3 on diagnostic tools for New Age science. And our first speaker in this session is Corey Wilness. Corey Wilness grew up on a farm and has a Bachelor of Science in Agronomy from the University of Saskatchewan. He has worked as a professional agronomist since 1996. At Crop Pro, which he founded and runs, he has 25 staff serve farmers in Saskatchewan with digital software, field scouting, and variable rate services. At Crop Domestic, 15 staff build and support a suite of patented soil mapping technology products with business partners around the world. He has founded SWOT Maps, Soil, Water, and Topology Maps, a unique map building module that takes multiple soil layers of data and turns into a single soil type map. So thank you very much, Corey, and we will let you share your screen and looking forward to your talk. And I will give you a 5-minute warning just by turning my video back on. If there's any questions, please wait till the end and you can put them in the chat or unmute yourself and ask directly.
Okay, can you hear me?
Yes.
Yes, we can.
Okay, well, thanks for having me. I'm interested to be here. I guess I'm sort of just a boots on the ground person. I'm sandwiched in between all you scientists, so I hope you find this interesting. I guess we deal directly with farmers with most of our tools, and I thought to kind of keep it simple, what I do is just give you some examples from a smart farm that we have here right at my home quarter in Nacum, Saskatchewan. It's a place we do tours and research and demonstration. So quickly what I'm going to go through here is I'm going to show you how we build these soil, water, and topography maps, or SWOT maps. We're going to soil sample them. We're going to put on a sulfur fertilizer prescription. We're going to build some SWOT water maps. Then we're going to show you a little bit about a SWOT cam that's going to map crop and weed populations, do a variable rate on-off fungicide prescription, and then show you some yield analytics. So SWOT mapping, as we call it, the primary source of data that we use is accurate elevations through RTK GPS or LiDAR, and then any type of EM or EC device. So this SWOT box system that you see here mounted on various implements is a Geonix EM38 or a GeoProspector's topsoil mapper, and it has its own data logger and communication system, and it sends all the data in real time to our servers where we can start to build maps. So this is the field here shown on Google Earth, and this is like one of my favorite map layers. It's just the water flow paths in the field. I always say water drives everything, and it's fun to see your water models over top of just a regular image. So I'm not going to spend a ton of time on each of these map layers, but just to show you some of the layers we collect. So here's elevation with flow paths. And now it's turned into topography. So of course now it's depressions, mid slopes, and hills. Before it just said it's high or low. And high or low doesn't know if it's collecting water or shedding water. So you have to turn that into topography. And then here's the electrical conductivity layer in the field, which is great for measuring things like textures, water, and solutes in water. And the challenge with this layer is all these things are mixed together. So requires some ground truthing to define why the areas would be high or low in EC. And then we can also use organic matter, or it's basically soil color sensors from remote sensing or from sensors that actually go into the ground. And in the end, all of these layers on their own are, relatively useless as a all-in-one map type. So we use our logic to convert all this into a single soil type map that depicts the field. So all the zone ones here in this field, we've categorized these as they'd be the most high and dry parts of the field. They'd be the coarsest textured, they'd have the thinnest topsoils, probably slightly eroded. And then the yellow zones, the middle is like the field average soils. And then as you get into the greens, it's where you're starting to collect water. They'll have thick topsoils, they'll have higher organic matter. So you can see how this sort of turns into what you'd call a soil type map. And this is just a screenshot of our app. So we have all our own software. So now the agronomist would take this soil type map and they would go and soil sample this field into zones. So just a little depiction here is this is the type of zone process we're building, where the most high and dry, eroded, coarsest textures, thinnest topsoils would be a 1, and then as you go down your slope and you start collecting water, you'd end up with thick topsoils. And of course, historical erosion has had a large effect on these landscapes as well. So these are just some screenshots from our app as we're going into the field. I've alluded to it before, but the goal is always to make these things very simple, very efficient and productive, and to keep the cost down. So we build a 10 zone map because it gives us nice fine resolution for building prescriptions on, but then we only soil test 5 of the zones. So for example, you can see all the ones here so all these little hills and areas with thin topsoils, the truck would go to each of these ones and sample 2 or 3 points, and so you'd have 15 sample points come out of those and go into one bag. So we actually have a project going on with Amina right now, and the Prairie Agriculture Machinery Institute and the University of Saskatchewan, and we're working towards like automating so many different steps that are required. So right now, today, what do? We have a person that drives around in a truck. It's got 2 different samplers. This one works really good in the mud, and it's sort of an automatic system that screws down into the ground. Here's a 0 to 24-inch soil core probe, hydraulic, and spots for the buckets for the soil. As you drive around to each of the zones, you put them in the buckets. Your map on the screen with your GPS, and we have like 13 of these trucks. So you can just picture for months and months after fields are harvested, you have these people driving around doing this process, zone sampling. Very time consuming, hard labor work. So just a couple little shots here of, well, what do we end up with in this field? So this is a 24-inch pictures of the soil profile. So our zone 1s, everywhere you go to a zone 1, this is what you see. It's got a sandy loam texture in the surface, and down at 24 inches, it's still sandy loam, and you can see, only 5 or 6 inches of low organic matter topsoil. As you move into the mid-slope soils, you start to see deeper topsoils and getting some finer textures now. And by the time you get to the zone 10s in this field, you have a loamy texture, clay loam down at depth, and now you have 18 inches of black dirt. And you can see, even as you peel with a spade, it's wetter, right? So this is the organic matter content from 0 to 6 and 6 to 12, just showing it increasing as you go across the field. So I'm going to show you, just to keep it simple, like we do variable rate everything. We do all the nutrients, we do seed varieties, we do seed rates. There's many different things we vary. But to keep it simple, I'm just going to show you sulfur. So if I go back here, I think we all kind of know how sulfur would respond in a field. So in this case, you have like these deeper topsoils with more organic matter. This has a lot more potential, of course, to mineralize sulfur. And when you do your actual sulfate soil test, 99% of the time what we find is these zone 10s, these water collecting areas with thick topsoils and higher organic matter always have the highest levels of residual sulfates also. You can keep cutting back here year after year and this never changes. It always has the highest level of sulfates. But in this case, you know, there was fairly deficient soils actually in the rest of the field. So let's go put on a prescription here. So this is our report. So this is the map here. Here's the soil test results. I already talked about the organic matter increasing as you go down the zones. I already talked about the soil sulfate levels. And so what we put on here was 3 years worth of fertilizer. We floated it on, so we have a 50-50 blend of elemental sulfur and ammonium sulfate. So at a field average rate, so this is say what a farmer would do if they weren't doing variable rate. He's going to get 90 pounds of actual S, 69 is elemental, 18 is sulfate. And remember, like I said, we're putting on all this elemental because we're not going to put sulfur on again till 4 years out. But we're predicting that the highest responses are in these zones 1 to 4. These thin topsoil, water shedding, low organic matter areas that test low in sulfurs. And these areas that collect water and have thick topsoils and higher organic matter, we're putting on very, very low rates. So then you load your prescription into, in this case, it's a floater. And as they go across the hills, they put on 200 pounds. They go into the depressions, they put on 42. Here's just showing the elemental prills and the ammonium sulfate prills. It's doing a nice job. And now we got some pictures here of the strip trial. So this is a 0 sulfur strip trial. And I've got screenshots here from my app that show here I'm in a zone 9. Okay. And then this shows here that there was no sulfur applied. So this is an as applied map. It shows that this was in an area where nothing was applied. And then these are the rates out in the field. So basically there's no response to sulfur here. There's no visual response, and at the harvest, the yield data showed there was 0 bushel an acre difference between the check and the treatment. Once we get to the mid slopes, you can start to see just a little bit of you know, some sulfur deficiency symptoms, but in general still looks quite good. So we're in a mid slope here now. You can see you're in the untreated check. And as we get now up towards more of these tops of these hills, these areas that are shedding water, and I say hills, but whenever people come look at the field, they're like, well, I don't really see a hill. It's just higher ground that's coarser textured and thinner topsoil. It's not like an obvious hill. Anyway, here now you can see, you know, visual symptoms of sulfur deficiency, and we're getting a 5 to 12 bushel an acre response in the area here in these zones with no sulfur. And there's some more plants up close. And it's interesting, so we did like zone tissue tests all across this field, and here we are, we've got our sulfur test saying it's sufficient. This is a common problem we have, is that, you know, because your biomass here is only 10% of what it was down slope, we can end up with smaller plants still showing up sufficient in sulfur sometimes. I just made a note down here. The nitrogen to sulfur ratio was 22 to 1. So we did suspect that, you know, obviously you're going to get a good response. But so just jumping into some water maps here then. So here's our same soil type map, our SWOT map for the field. You kind of got a picture now in your mind of how this looks. And now to do a water map, what we did is we're installing soil moisture probes in the soil down to 100 centimeters. So we put one in the top of the hill here, what we is perceived to be the driest part of the field, one in the mid slope, one in the depression. And here's an example of the station that sends the data remotely with it's a John Deere soil probe in the ground here. So we take 4-foot samples, and every Every foot we do organic matter and texture by particle size analysis. So I already showed you these pictures here of the soil types in each zone. And of course, so what we're turning this into is now we don't just have a single point soil moisture reading. We have a map of it modeled out to the whole field, because we know that these zone ones are all similar, right? When we've gone to them, they're all have very similar textures. They have similar organic matter contents, similar depths of topsoils, and so they have similar moisture holding capacity. So now this is the moisture holding capacity down to a meter on this field modeled out. And then here's just a quick screenshot of the app showing at June 15th that the zone 1, the tops of the hills had 86 millimeters of water available, the mid slope had 156, and the depressions had 218. So now here it is modeled out across the field, and we make these maps daily. So a farmer that would subscribe to this service, he would have this map every day. He would see how much water is available. And so you can see, of course, that if this is June 15th and you've only got, 50 millimeters of water available or something on tops of these hills, that what's the point of adding a fungicide or top dressing, extra fertilizer, that types of thing. So that's gives people a good tool to make more, relevant in-field decisions, that they could vary the rates on. So another piece of technology I want to show you is a SWAT cam. Now we're working with Abdul Bays out of Regina, University of Regina. Normally what happens is an agronomist drives to the field, walks or takes a quad, does a few subjective zone counts of plants, and then takes some pictures, and then this is how we analyze our plant mortalities by zone and seed rate decisions, those types of things. But it's very time consuming. Here again, we'll have like a dozen agronomists driving around for a month, and you can't cover most of the field, and you can't even cover all the farmers' fields. It just takes too much time. So we built this simple app called the SWAT Cam. It's just shown on a couple sprayers here. It's just an Android smartphone app that requires no operator intervention. It'll start up on its own, and it takes an image every 50 feet. So here's an example of my field here with the image capture. And then Abdul and his team they take our images, and of course they're using machine learning to model what's weeds and what's crop. So this is pretty simple stuff, really. Like, we've done, I think, 15 different crop types now, and we're not doing a lot of identification. We're just building the models out so that we can no longer have to go to the field to do our crop stand population counts and, some general weed counts. So here's some picture from the field here. So I'm standing on, it's almost kind of like a little hill here. So you can see on the SWAT zone map, it's maybe a zone 3. So it's not like the most high and dry part of a field. But you can see the weed leaf area in this from the SWAT cam map. So this is the weed map now that we created. You can see there's not many weeds here. And actually we did a prescription on this field. So we varied the water from 10 to 12 gallons an acre based on weed densities. You can see we applied low rates here. The lowest rate was that 10 gallons. Now this is just like maybe 100 feet away. So I was just in this spot where I showed you. Remember I showed you on the SWAT map, it was right here. Now you just going down the slope a little bit. Now here's a zone 10, it's a depression soil. And you can see it's loaded with weeds. It's loaded with wild oats. So you can see now our weed leaf area map showing really high populations. And now you can see on our spray prescription, we're applying the highest rates of water. So we're putting on basically 20% more chemical here. Yeah, and this is just a quick prescription showing what we did there. And then here's an as applied map. So I've showed a few as applied maps. This is just what the sprayer did. So we make a high resolution map for the sprayer for the prescription from 10 to 12 gallons. And then here's what the sprayer did. It was a 60-foot boom. So, it generally works good. A lot of technology yet is just sort of the width of the implement, so it's not perfect, but. And the end goal here is just to, with a few farmers, here's your leaf area now. We've got thousands and thousands of observations. So the blue here is the crop and the yellow is the weeds. So weeds are way more prevalent in the depressions on this field, very few weeds in all the hills. So just to finish off here, a quick fungicide prescription. Why I thought this was interesting to show you was that we did it by zone. So the tops of the hills here had the least amount of sclerotinia infection when we were getting ready to check it for spraying. And the zone 10s actually were kind of poor too. The crops were kind of thin there, it was a little bit wet. And so most of the high biomass and the high infection rates was in these mid slopes to well-drained depression soils. So we just built a prescription here from some July satellite imagery. We put no fungicide on the areas that were poor, so that 17.5% of the field got nothing. And then the areas that were low biomass, we put on the low rate, and we put the high rate of fungicide on the high biomass areas. And so, yeah, we did this actually with the plane. So this was the prescription that we sent the plane, and this was the as-applied map that we got back. Now there's a power line in here, so don't look at that. But in general, it worked really, really well. So you can see all along here, we're supposed to put on nothing, and you can see the plane, matched that pretty well. You can see in some of our zero strip trials here, it put on nothing. Ground rigs would be a lot better, but we kind of wanted to showcase using it with the plane. And my last slide here on yield analytics. So we pull data from different yield mapping systems, and we summarize it by zone and compare it to our target yields. And there's lots of other things we do: protein and yield relationships, nitrogen use efficiency, water use efficiency. But yeah, and I kind of alluded to them as we went along. So just my summary slide here. Yeah, I just wanted to showcase today why we feel that soil is the foundation of a precision agronomy program. And I think I've said all this stuff already. Are there any questions?
All right, thank you very much, Corey, for an excellent talk. Very nice to see the work that you're doing. And you're perfectly on time, so we've got 5 minutes for questions. If you have any questions, you can already see in the chat. Parajita, if you'd like, you can unmute yourself and ask directly.
Yes, Corey, really wonderful talk. And this, there couldn't be any better opening talk for this session, I think, because as you said, you really went to the field and diagnosed how the field is doing. So yeah, I just had this quick question. So whatever you showed in terms of resource management in the field, so are they also sort of context aware? Like you were showing that, wherever the field is sort of depressed, the weeds tend to grow over there, and so you obviously spray more. But this spraying, this action of spraying, can it be done sort of automatically, or do you actually have to intervene all the time? You get my question?
Yeah. So there are some manufacturers in the world working on real-time weed identification, like imaging it in front of a sprayer boom and then controlling the sprayer to like nozzle by nozzle spray weeds. It's not commercially available yet. Yeah, ours is more, I guess you'd say, simplistic. We're really just using it for crop and weed populations, and it could be used in the future and stuff like that. It's like a really cheap tool. But yeah, with ours, basically you'd have to build the map first, then go back and apply some type of prescription.
But so essentially, theoretically speaking, it can be done. As maybe a futuristic little bit, but it can be done.
That's correct. Yeah, it can be done.
Thanks, Corey. Thanks.
Okay, thank you. We have another question in the chat. Joshua, you can unmute, or I can read your question. Go ahead if you'd like.
Yeah, I can ask. Hi, Corey. Thank you for that very nice talk. I had a question. You use data obtained mainly from the field, but you also use some satellite data. So I was wondering, how do you choose how to combine them or decide which one to choose? I know you skipped through many things, so I was just curious to know what the strategy is.
Yeah, that's a great question. And like we always sort of separate what I'd call soil potential maps from what yield potential maps. So satellite data and yield maps to me are they're great tools for measuring the sort of crop response at a specific point in time. Okay, so satellite data, yes, I think that's good. For example, I used it for my variable rate fungicide application because at that particular point in time, it's a perfect match to the growth and biomass of the field. Now, if I didn't show the data, but if I showed you the satellite data from June 15th, the crop is tiny. And so basically I end up with a biomass map of weeds. So it matches the weed map, right? So, and for when it comes to soils, like using remote sensing, you could use it for, say, soil color. Like if there's no trash on the field, you could use it for soil color. But in general, I think mostly satellite data to me is like for in-crop stuff. It's for measuring things where you want to measure a crop. Whereas soil techniques are all for, things that are going into the soil. There's no crop in the field yet. We're putting fertilizers on. We don't know if it's going to be wet or dry. It's for soil sampling and things like that.
Okay. So you're looking at the soil versus the crop.
Yeah.
Okay.
Yeah.
And the second question I had was the LiDAR. So you actually you take a LiDAR on the field on top of those, on the tractors, or?
No, in this case, LiDAR is all data that's been collected with planes.
Planes.
Okay, so like Alberta, the whole province is covered with really good elevations done with LiDAR.
Yeah. Okay.
And Saskatchewan isn't. There's some areas of the world that have really good LiDAR, some don't. But yeah, it's mostly just elevations with planes.
Okay, thank you.
All right, thank you so much, Corey. There is one more question in the chat, but to keep us on time, maybe if you don't mind, I'll let you answer that in the chat that you can see from Brittany.
Sure, yeah, thank you.
Thank you. So we'll go on to our next speaker now. Our next speaker is Dr. Jean-Claude Kiefer, who is a professor at INRS in Varennes, Quebec. His research interests include plasma physics, ultrafast lasers, ultrafast and high-intensity laser matter interaction, ultrafast X-ray sources, and their applications to health science, as well as dynamic imaging of complex systems and particle acceleration. He is currently a member of the board of the Canadian Light Source, and he is the science and technology advisor for laser and optics of the president of the Aquitaine Region Council. Apologies, my cat has terrible timing of jumping in. So today, Professor Kiefer will be speaking to us today about laser wake field driven X-ray sources in Canada, a brilliant future for agriculture and global food security. So thank you very much, and I will let you share your screen, and please put any questions in the chat.
So thank you very much for this invitation, and I'd like to thank Amina in particular. It's very kind, and the organizing committee. It's an opportunity to present what I am doing with the colleague at Global Institute for Food Security in Saskatoon, and in particular with Émile Alain. So that's I'm not doing that alone, of course. It's a complex program, and over the years we have been developing this new technology, X-ray technology, with our colleague in Edmonton, with Bob Fedoseyev group at the University of Alberta, so the people at the University of Saskatchewan, but also with a French colleague and with some group in Russia. And I am very privileged to be able to still work with Jean Roux Professor Jérôme Roux invented this kind of laser that I am using, and he has been sharing the Nobel Prize in 2018 with Donna Strickland, who is professor at the University of Waterloo in Canada. So that's a long shot and long collaboration with many people, and I would like to recognize that. So this, my involvement on the plan, so I will ask for some indulgence because I am not a plan person, you know. But my involvement is back to 2013 when I started to work with the people at the University of Saskatchewan, and they established in 2015 this Plant Phenotyping and Imaging Research Center, the Global Institute for Food Security, with aiming to correlate the phenotypic expression with, you know, the environmental stress. So we started to do a lot of work in terms of imaging and using X-ray for understanding plants. So this, the initial problem that's coming from or set up by the Global Institute for Food Security is simply to try to see how the roots of a plant are interacting with the soil. In other words, can we see the interface, and can we see the dynamic of the interface and the interaction with the soil, and in situ eventually. So it's an interesting problem, and of course the idea is to use a penetrating radiation and try to visualize on dynamic what's happening. So we started this this program, and the idea was to build a new type of X-ray machine for this problem. We were thinking to develop a new technology to help to deliver innovative solution, helping to realize some production of globally sustainable food. The idea was also to move from the concept to a commercialization. And but the basic point that's trying to develop a new technology is to go inside the farm, and that's not a trivial goal. So we have been developing this new technology, and in fact, maybe the question that you may ask is, why do we need to develop a new X-ray technology? You already have this conventional, you know, the conventional X-ray tube, which is already existing on the market. It's a low cost. You have the synchrotron, which is a fantastic tool. And so why do we need to develop something new? And in fact, the problem is that the acquisition speed, which is actually too long with conventional the conventional technique, it's in a few minutes range. With a synchrotron, it's extremely long. It's in the 1 hour range. So the idea is that you need to try to have a very fast acquisition speed, because you want to do fast scan for the for helping the farm to understand what they have. And so we decided to try to develop this technology, and the basic idea was to develop this what we call the laser wave field acceleration driven X-ray source. And this is an example. Of course, it's not a machine right now. It's really still a laboratory experiment, but we already produce very nice spectra, and we produce very nice spectra, and actually you have this kind of synchrotron type of spectrum that's producing some kind of 20 microjoule at 20 kV, and it's actually one of the brightest source of this kind. So you have the plant on the left, just to give you an idea of the scale. And this is a kind of source that we are using. This is a cone angle X-ray source with a 50 millirad of divergence. And that's actually, it's a very interesting source. So you say, okay, fine, we have a nice source, but what do we do? And if we want to understand the interface, then you need an imaging method. And what we have been developing is inline holography. And thanks to Augustin Fresnel, who he has been working before the X-rays, of course, but he has been developing all the theory of the diffraction. And the idea is that if you have a very small X-ray source, a small source, then you can recover the coherence or some spatial coherence. And so this holography concept was developed by Denis Gabor in 1948, but it wasn't demonstrated with X-ray at the European Synchrotron Radiation Facility only in 1995. And what we are looking at, if we calculate correctly the distance between the object and the source, you can enhance the edge, and what you can see is really the interface between the object and the external world. So you are in a near field Fresnel diffraction, and this is what we try to do. So in other words, we are doing the imaging with the phase. So just an example of the what you can obtain with such a phase imaging. If you take a cell of nylon fiber, which is a very simple object, then this is what you obtain on the left of the screen. And you can see you have a white fringe, and the white fringe is an indication of the phase. So you can reconstruct the information by using an algorithm that you can reconstruct the object. In that case, it's a 4-micron resolution, or you can experimentally retrieve the phase, and the phase gives you information on effectively the interface. So that's what we are doing with this kind of source, which has a 2-micron X-ray source size. And that's a few examples of what we have been doing with laser-based different inline X-ray holography imaging. I started with my student nearly 20 years ago on this domain. The idea was to develop a technique to have a very low dose. Initially, it was for the breast cancer imaging, and progressively we go to trying to develop a high throughput and portable system. And so that gives you some example of what we did with small animal with various objects, and progressively we move to plants, to plant imaging. This is an example of some images that we obtained, of which one is LC, the other one is SICI. You have a 4-micron resolution, but the interest is that you get the image in one laser shot. So when you have a laser with, which is doing several shots per second with a high rate of, we are working with 2.5 shots per second, but you can work up to 10 shots per second, 10 hertz. Then you can generate a lot of image, and you can have a very nice idea of what's happening. So this is a simple experiment because it's above soil. It's another kind of experiment where we have been looking to the hydration, and by doing experiment before hydration and after some time of hydration, so you can see this the network of channel, and that is this network is pumping the water, and then you can understand how the plant is using and pumping the water. It's the water is going through the inside the plant, and also on the edge and on the surface. So that's another example of what you can do with the technique. But we have been doing another step and trying. What's very interesting is to understand the roots. So that's an example of image obtained with different plants. In fact, the plants are prepared at the University of Saskatchewan. In that case, that's different genetic line of plants, and they are sent by plane to the botanical garden in Montreal. Then they are taking care of the plant during a couple of days, and then I'm taking the plant at the botanical garden, go to the laboratory, and we start to run experiment on imaging. So you can reconstruct this kind of plant, so you can see the difference. And the idea was to see the interaction of the nodule with the soil. But in this game, the very difficult aspect is how to produce a very stable X-ray source. I think that was the most difficult problem that we have been facing, and this is an example of phase contrast tomography. We have been running the X-ray source for a long time. It's a 20 kV X-rays, and you can see that we have been able to obtain a very nice stability, but also a very nice reproducibility of the noise and signal-to-noise contrast. So that's what we are working actually, and of course this is with 20 kV and 2.5 hertz. So that's we are still a bit far from a real machine in terms of solution readiness level, not technical or technology readiness level, but solution, because we try to provide a solution for the real farm and people in Saskatchewan. We are somewhere where we have been able to integrate and test the basic solution with the component, something between 4 and around 5. It took a lot of effort and a lot of investment to come to this solution. What I would like to continue, it's really to go to the prototype demonstration, and really in some experimental farm, as an example. Of course it's a question of dollar. If I had the correct amount of money tomorrow morning, I should be able to do it in 3-4 years, the maximum 2023 or 2024. But that's we already established a consortium with industrial partner, but that's still a complex process. And we came to a design for a new machine, and this design, of course, we will have this micron resolution, because we have a 2-micron source size, a very large field of view. Well, it depends, of course, of the magnification and the distance between the object and the detection system. In fact, we are working right now to increase the X-ray energy. It's going to the 50 kV range. We increase the acquisition speed, and we are working at 2.5 hertz, and we are planning to go to the 10 to eventually 100 hertz repetition rate. We need to decrease the footprint, but that's not a problem. The real difficulty right now is that the technology is it's expensive, and it's not on the short term. Decreasing the cost will be really a challenge. Now we start to integrate the deep learning, and we have been working with between 1,000 and 5,000 images per hour, depending on the way we are doing experiment. And we would like to see if we increase the repetition rate, we will increase the rate of image per hour up to 10,000 or a few 10,000 images per hour. So it's really, we need to manage the data correctly and understand correctly. So we have been experimentally defined the scaling, so we know how to go from 20 kV to 50 kV. That we published that recently, and that's part of what we call our MX machine, the design that we did. And again, it's it's some kind of synchrotron-like spectrum, but we can filter, and that's something which will be very practical for very thick sample. To conclude, I will just stretch something interesting. That's we have been working a lot and generating thousands of images with plants, roots, various quality of soil, with genetically modified plant or line. But there is a common challenge for different fields with the same technology. That's looking to the dynamic of interface between a system and its environment at the molecular or cellular level, or you know, micro system. It's the same challenge for early breast cancer detection, or the detection of mini strokes with looking to brain macrovasculature. So it's something which is extremely powerful technique with a micron range resolution, and that's something that we already started to work on the early breast cancer detection besides the plant application. Just one word on what on LaserNet US. We have been welcome as one of the facility in 2019. We have been welcome in the LaserNet US, which is regrouping all the big laboratory in North America, of the big laser laboratory in North America. And we are the only laser facility in Canada to have been in this network. The network has been created in 2018, and we just finalized the first round of selection of the proposal. So the advanced laser light source in Montreal is open to user, and effectively the Betatron beamline, or this X-ray imaging beamline, is actually available. We managed to be able to offer something like 10 weeks per year for the user if they want to come, and we have already received a proposal. The LaserNet US is led by Félicie Albert at the Lawrence Livermore National Laboratory. So that's of course we had a lot of funding for this initiative, and that's part of the Canadian system, and all the institutions being helping us. So that on that, I'd like to thank you for your attention.
Thank you very much, Jean-Claude, for a very interesting talk. I will open it up for questions now. If anyone has any questions to start out, please feel free to unmute yourself, or you can put them in the chat. In the meantime, I'll ask a question to begin with. So I'm curious about the scale of a prototype that you're planning or for the long term in Saskatchewan. What do you think that would look like, or what sort of system do you envision?
It's actually the design we have is relatively complex, but it's inside a container. It should fit inside the container. The laser system that we have is already extremely compact. And I believe that the more complex part to deal is the compressor of the system. But everything should enter inside. I had a nice image of a container. That's, but it's really a challenge to arrive at this level. We see.
Yeah, a challenge, but very exciting to achieve that.
Yeah, well, it's been taking something like 10 years to arrive at this level, so it's a bit long.
Yeah, many advancements along the way.
Yeah.
I think maybe Bob has a question.
I was going to ask Jean-Claude, you're doing 3D tomography images now of the roots. Yes. There? Or is that the plan also to do rotating 3D?
Yes, we have been doing 3D tomography by rotating the plant. In fact, we did something like 750 760 images in five minutes. That's the best we have been able to do with 2.5 Hertz and 1 image per shot. And that was working relatively nicely. So we, it's the group at the University of Saskatchewan is doing the reconstruction. So we provide the data and they are doing the reconstruction and playing with that. But we have now a nicer stability. The real problem was to achieve the stability of everything, of the laser system and stability on the pointing stability and the energy stability. So it's working.
Very good. Thank you.
Go ahead, please, Mohammed. Thank you.
Thank you, Jean-Claude, for the presentation. I have just indeed a little bit, if you can comment on that, what the advantage of using a laser as a source, for example, for the X-ray that you're using by comparison to the conventional one that use, like, for example, a directive source or electron beam or others. So what is the advantage of using the laser to produce the X-ray?
So that's the first advantage that we have a cone beam. So we have a divergence of 50 millirad by 50 millirad, which means that roughly at 1 meter from the object, or at 1 meter from the source, your field of view is something like 2.5, 1 inch, which is very interesting because you have all the photon in this cone beam. Then you are, so this is the first one. The second one is that it's really a lot of photon. It's actually one of the brightest source in the world in this kind. And it's something like 10 times brighter than the usual K alpha X-ray source. So if you are, and that's why we demonstrated that you can do 1 image in 1 shot. So this is particularly interesting because then you can do the tomography extremely on a very fast acquisition time. And this is the big advantage is really to have a fast acquisition state, a fast acquisition speed.
Okay, thank you.
Because if you compare with the synchrotron is a very small spot. So you need to stack a lot of image, and it's taking a long time to get an image, a very large image. If you're taking a conventional X-ray tube or whatever, then you have the emission is in 2 pi steradian. So it's why it's so interesting.
Thank you.
Thank you. We have time for another question if anyone would like to ask. Parajita, are you unmuted or no? Okay. So I guess I'm curious, what are the smallest scale features that you might be looking for in these plants, and how does that compare to the resolution limits of the Betatron?
Actually, it's if you want to see the interaction between the nodule and the soil, it's in the micron range, because that's a micro. It's regulated by the microorganism, if I understand something in the plant, and that's in a few micron or micron range size for the microorganism. Actually, we are limited a bit by the detection system and by the pixel of the detection system. The source per se is the source is 2 micron, between 1 and 2 micron in diameter. But we are probably able to do better and to get a few micron. We are not far from the resolution that we need.
It's very interesting, very well matched. All right, well, thank you again for a very nice talk.
Pleasure, it's a pleasure.
And we will move on to our next presentation now. And so we have actually a tutorial and a live demo that is next on agri-photonics, spectroscopy and imaging techniques in agri-food, with a live demo of fluorescence, Raman, and terahertz spectroscopy and imaging. And this will be given by Dr. Parajita and Bandyopadhyay and Dr. Pramit Chowdhury. So Parajita, who's also a co-organizer with us, is the terahertz vertical coordinator at the JATC IIT Delhi and connects closely with the academic research and industrial efforts in establishing greater footprint of the terahertz technology in India. She earned her PhD in applied physics from NJIT Rutgers, USA, and worked in Germany and Washington State University as a postdoctoral researcher on terahertz imaging, pump probe terahertz spectroscopy. Currently, she is involved in charting the technology roadmap for terahertz field in India. At the same time, she is passionate about agri-food research and green energy initiatives. She was the reason why we're able to host this conference, actually. So very happy to have met her and seen her invited talk at the CLIO conference last May. And Dr. Pramit Chowdhury is a professor in the Department of Chemistry at IIT Delhi. His research group focuses primarily on the structure and dynamics of proteins in crowded milieu. His main interest is in understanding the crowded milieu in a better way by employing a host of ensemble and single molecule-based techniques, with fluorescence being the main spectroscopic tool. All right, so thank you, Aparajita, and I will let you go ahead.
Thank you so much, Amina, and thanks for the introduction. And well, Amina was too generous to say that I was the reason that this could happen, but I think, I mean, it is amazing to see that not only the speakers, but there are also so many participants who are joining us on this virtual platform for all the sessions. And in spite of these weird hours, I mean, both here and over there on the Canada side, and in fact, all over the world, I would say. So I'm sure actually it is our zeal and our interest, our passion for this particular topic, which is actually driving us. And I'm sure that in future, we will achieve even more. So with that, I will, present this. I will start this presentation. So, so far, we have been listening to different different groups saying what they are doing in this regard. So, for the first time, I think we are now going to talk about the actual, sort of laboratory based spectroscopy and imaging techniques. Which collectively we see is actually termed as agri-photonics. So I am Aparajita, and also Pramit will also be joining soon. He would be giving the next part of the tutorial. But so in the first part, I will talk about, in general, what is agri-photonics, and also later on in that, that will be followed by live demo, not exactly live, but because we actually also felt that there were issues with this virtual platform, especially Zoom. It was creating so many problems. So we actually our students pre-recorded these sessions. So Raman spectroscopy will be given by Diksha, whereas the terahertz spectroscopy and imaging demo will be given by Khushbu. And then obviously, when Pramit will be presenting, then he and his team will be also giving a pre-recorded demo of their steady state and time resolved fluorescence spectroscopy. So I just want to, because I just gave you so many bunch of names without any faces to put on them. So as you know, we Amartya and myself, we collaborate very closely. And so we have two labs, high precision spectroscopy lab and terahertz imaging spectroscopy laboratory. And this lab where actually I'm sitting right now, you can see the lab in the background. So this is actually established by our center, JTC, where I work. And so this is the entire research group. Khushbu, as I said, she is one of the senior PhD student. Diksha is going to talk about that, Raman. And then we have Mayuri, Urbi, and two newcomers, I would say, Uzair and Karthik, who are also actually present in the participant list. I can see that. And our collaborators are actually all over the world. So I should actually talk about first Alex, because he is actually a long-time collaborator now. He's in University of Queensland, a great guy. He works on QCL, terahertz QCLs, and in fact, Mayuri and Urbi, these two students, they come under the UQDR program that our IIT Delhi is already running with UQ. And you already have listened to Yash's talk. last night, or rather in the morning for my Canadian colleagues. And obviously, you all know Amina, our wonderful chair of the session, and Pramit. So he's the person who would be giving you the next part of the tutorial. And also, you listened to Shudeshina's talk on thin film batteries last night again. So moving on, I thought I rather than giving you a sort of a bulleted points outline of the talk, I will give you a sort of a visual outline. So the very title of our conference is basically, we are talking about, spectroscopy, I mean, science and technology of new age. And we also said, acquisition, analytics, and adaptation. So I thought it took me some time to put this together last night, but I thought we should actually highlight that, this entire picture, it's actually so massive, so broad, that to put your particular work, or say for that matter, for this particular talk, where I am going to talk about our results and slightly that part, we need to sort of see the entire map, what we are talking about. So you actually heard Alok's talk, yesterday, and I think he actually gave a quite a elaborate landscape of applications in this particular field. But I think the most the key part was actually the part of where he was showing that Google has already launched so many, this Google Earth machine, then this plant buggy, all these sort of things. So they are doing sort of network of sensors, while our next speaker Jayshree was talking about her multispectral camera on CubeSats and LiDAR. So these are obviously large scale systematic tracking. And then Scott actually talked about soil and emission. Again, very large area sort of optimization. And then Yashwanti talked about small scale, laboratory scale hydration and phenotype trait determination. And obviously, it is intricately linked to the data, how she analyzes that to understand the sort of the genetic pathways, the proteins that she is trying to access. And then obviously Jack's talk, Jack's from Logiag, they have already done amazing work on app-based decision dynamics services. Again, I will say a large-scale application. And obviously their application was possible because they actually did laboratory scale LIBS, laser-induced spectroscopy, the kind of thing Amina is also doing, and even I think in some sense heart of everything lies with that data acquisition, what we are talking about today. And obviously Corey also spoke about today in the first talk of the session, sort of the field level management, and also again sort of the large scale data, while just my previous speaker, Jean-Claude, talked about a completely, because all these time we were talking about, using maybe some laser, or say some spectroscopy, or say some multispectral camera. But now he's saying that, using a laser to produce this X-ray. And see, also think about this, the kind of resolution, because basically the unit of your sample or the target can actually vary, say, from Jayshree when she's looking from her multispectral camera. Instead of, say, a leaf or even a microorganism, she's actually looking at a bunch of plants, maybe a part of the field. While Jean-Claude, what he was talking about, actually microorganism, because he can actually look into that much of fine resolution. So depending on what sort of diagnostic or what sort of data that you are acquiring, you can sort of tune this resolution all along. So this is what I am sort of talking about today, the spectroscopy and obviously the imaging. These are all near field imaging, nothing far field. And so I will talk about the sort of the facts of the agri-photonics, why we are actually here, what are we trying to achieve, and sort of what are the elements of these area, and certain pathways. And also, I mean, we shouldn't only talk about, what could be, or what is already out there, or things like that. We should also be equally pragmatic to talk about the roadblocks. And then obviously I will talk about Raman and terahertz physics a little bit, because then the demo that would be given by Khushbu and Diksha, basically the instrumentation of that part, it would be well understood by most of the participants, I hope. I will not go into the the nitty-gritty of the physics, but just the sort of the basic parts. So please hang on tight. I hope I can sort of do a good job with not getting into any equations and things like that. Okay, so as I said, let us sort of take back a moment to sort of verify that what we are doing right now, how, I mean, how we sort of, sort of justify that whatever we are saying, that this is critical for the entire world, not just one part of the globe, but in general, it is needed that we talk about these problems. Because first of all, I'm just giving you a sort of the summary of the problems over here. We know that we are fast, I mean, very fast manner, we are depleting our world's land surface, land resource, as well as blue water resource, freshwater resource, I mean. And most of these resources, as Olok also pointed out, instead of nourishing the humankind, we are actually feeding the livestock. So that is one aspect of it, which is actually, I mean, when you think about it, it is actually part of the problem. And then at the same time, 12% of our world population is still undernourished. And yet, as I'm showing over here, that about 90% of the entire world farming operation is run by basically families. So they are small scale owners of land, and they are producing actually almost 2/3 of our global agricultural overall products, like all the food and everything. So that is kind of thinking that if we have to come up with a set of solution, then a specific solution might not be equally effective everywhere. A solution set that is effective in Canada might not at all work, say, in a place like India or China. Because remember, as I'm showing on this graph, China and India, they actually account for this largest number of family-owned, or basically less than 1 hectare of farm size. So just keep all these sort of facts in your mind, so that as we move on, you can understand why we are talking about all this. And just so you all, just so that all of us are on the same page, that by 2050, we will be in a world population of 10 billion. Staggering. So what are the elements? So actually, by now, I think all of you know that the precision agriculture, what we talk about, actually sort of composed of 3 specific parts, like obviously the sensing part, which is, I'm talking about the agri-photonics, where you're actually sensing certain things. And then obviously the data analytics, the processing, and all these sort of thing. So, and obviously the information technology, the AI, the big data, and all these very nice people from Google, all their their sort of the image processing, their big data analysis, or AI-based analysis comes in handy over there. And then obviously we also have to thank our mechanical engineers, advanced engineering, basically CPS people, who can actually build basically heavy equipment, industrial heavy equipments, agribots and UAVs and all sorts of things, which actually sort of implement the whatever we are trying to achieve. Because even if you have the sensors, there's actually ground-based sensors or multispectral camera and things like that, you won't be able to use them unless you have the tools or the equipments to actually sort of make them useful in the field, right? So all these are equally necessary, and they need to work in tandem or in in a synergy, so that the overall goal of a successful yield map, as Corey was pointing out, there is what they do is that they have several types of maps to begin with, but I think one of the sort of the ultimate goal is, in certain sense, in precision agriculture, is to have a successful yield map while sort of optimizing the use of resources. And by that means resource of every kind: land, blue water, chemical, pesticides, everything. It's better that you use organic pesticides and organic herbicides or organic fertilizers. So ultimately, also, this entire thing also needs to be connected pretty robustly, I will say, with analytics driven. That means, all these Google guys, whatever they are doing, because unless we have these yield maps, connected with our GPS tracking system and weather maps and everything, then the farmers are actually won't be able to make their production decisions in the nick of time, to prevent any loss because of, say, a sudden weather or climatic issues, or say some onset of pests or parasites. So they need to be basically, they need to be in full control in certain sense, right? That they know that what is expected and what is going to come their way. So now I will suddenly sort of, from the big picture, I'm now sort of zooming onto that, as I said, sort of the small scale part. So the sensing part, as I say, is the agri-photonics of that precision agriculture, and these are the different pathways. That means you can have. I have only listed, maybe 1, 2, 3, 4, 5, 6 types of spectroscopy, but actually there are so many different kinds of spectroscopy out there. Even with fluorescence spectroscopy that Pramit will be showing you later on, there is also laser-induced fluorescence spectroscopy. Similarly, there is not only Raman spectroscopy, there is coherent anti-stoke Raman spectroscopy, and so many different, versions, so many different, not version, I would say, types of different spectroscopy, where obviously the physics of the spectroscopy, the physics that drive the spectroscopy technique, they are definitely different. And that's why the ultimate outcome, that means what you can sense, is slightly different. So like, as I said, that at least in this first part of my talk, I will be talking about Raman spectroscopy and terahertz spectroscopy. And these two typical types of spectroscopy, I have actually sort of enlisted what they can and what they cannot, and where they are good and where they are not. And so in some sense, both Raman and terahertz are good in most of the, agri-food applications. Raman is extensively used for food quality monitoring, as well as, sort of even in soil sensing, to know what are the kind of microorganisms are there in the soil and things like that. While terahertz is, still terahertz is not an established technology, remember, so it is also very, sort of aggressively being pursued for irrigation and water quality management, because as I have pointed out, that it is extremely sensitive to liquid water. And at the same time, it also has spectral signatures for most biomaterials. So moving on, as I said, I also need to talk about the roadblocks. So in terms of photonic technology in agri-food, the biggest problem is the cost. As we know, any photonic technique, it's costly. because you have lasers, lens, this and that, so many different, active and passive optical, components, which actually are very costly. So with that cost in mind, you automatically ask yourself, does it actually add value to my application? Does it actually give me that much of sensitivity, or, basically sort of, I mean, why should I at all use it, right? That is the first question that comes to mind. And obviously, competing technologies that are already out there, they are comparatively easier to use for the user because they have been using this for a long time. And sometimes there are also issues in implementation because it is most of the times they are slightly complex in nature, the photonic tools. And under actually certain conditions, because a field by itself, farming field, agricultural field, it tends to have so many parametric variability. And just because photonic technique by nature, it actually senses too many things sometimes. So the overall sensitivity goes down when you have these sort of variabilities in the condition where you're trying to sense. And also a lot of people get queasy whenever they hear the word radiation. Oh, something is wrong, there is radiation out there, so we are not supposed to go there, things like that. So that safety concern is also there, and so forth. There is a problem with the compatibility of existing technology platform, and customizability. As I said, that our end users are, after all, the farmers and basically the farming say unions. And depending on where they are, whether they are from India or Canada or China or Africa, things will change and they need to customize depending on their end user applicability. And sometimes photonic technologies, they have very limited customizability option. So that is one major issue also in applying these photonic sensors in the overall scheme of precision farming. So I have just given you this cartoon just to show that, using all these some established and some emerging technique, spectroscopic techniques and imaging techniques, you can do so many different kinds. I mean, you can think of so many different kinds of application, and not just in terms of field or food, but actually throughout this entire chain, from farming practices to food supply chain. Basically, I'm talking about, food quality monitoring and all these sort of things. Also food safety, again, the same thing. Not only that, we can also think of in terms of how to reduce our wastage, our, whatever we are throwing out, that shouldn't be the case. And also, how can we reduce our uses of chemical pesticides, microplastics, so that after all, our biodiversity, which is actually, we sometimes do not recognize that, comes very handy to the overall maximized yield map. Because this part actually was sort of dwelt up in by Scott yesterday, where he was talking about agroforestry. So all these different elements are already there, and all things considered, there is actually, the sky is the limit. We just need to be sort of innovative. So now a complete sort of phase shift. So now I'm going to enter the physics of the two techniques that I'm talking about. So for many people, if they're getting confused, what terahertz, what is she talking about? So terahertz waves are sitting in between, it's sandwiched between infrared and microwaves. I'm sure IR and microwave are easier to recognize in certain sense. And this is actually an extremely low energy radiation. So no, hey, there is no chance of getting any irradiation or any trouble with this terahertz waves, because it hardly can penetrate your skin. So whatever it is doing can only any damage up to your skin skin level. So it is actually biologically safe. And again, it has spectroscopic specificity because of molecular resonance absorption. Basically, all vibrational states, rotational states, torsional states, all sorts of, basically freedom of movement that you can associate with a molecule that's there in the terahertz range. And at the same time, terahertz can go through, not, it's not absolutely transparent, but limited opacity, I will say, through most of the dry dielectric materials. By that, I mean paper, plastic, cloth, wood, all these sort of things. Okay. On the other hand, I think Raman is a more established technique, and people kind of know what Raman is. So it is not an absorption physics. Remember, it is actually an elastic scattering physics, where you are not sensing the molecule directly, but rather the bonding groups, and that is why you have overtones as well. And basically, you can think of it like this. It is like, if there is like a dipole sitting out there, when your laser, basically the probing laser, whenever it is approaching that dipole, the induced dipole, how far, I mean, the acceleration in the changing of that induced dipole moment, that is what is the measure or the cross section, Raman cross section of that bonding group, right? And the major trouble with this particular spectroscopic technique is that since this inelastic scattering always comes with a huge number of elastics part of the scattering, or the Rayleigh scattering. So as I'm showing over here, you need to put a filter which actually removes the Rayleigh scattering, and only 1 in 10 to the power 8 scattering event is what you get as a Raman scattering. So you can readily understand the main hurdle, or the main fight, is to get that very, very small signal in a sea of very big signal, which is caused by the Rayleigh scattering. So, but one thing is that both these spectroscopy, you can also obtain a terahertz image or a Raman map through single pixel imaging technique, or using raster scan method. So that is again a system thing that we use. So quickly, I will just give you a sort of, as I said, I will not get into the physics, like the elaborate physics of it. It is just that in the terahertz time domain spectroscopy, instead of intensity measurement, we actually measure the electric field of the terahertz. And that's why we get twofold information, both amplitude and the reference. And you can do either material identification or quantitative analysis. And for the actual sort of the tutorial, I will highly recommend this particular journal. Do not think that this is a very technical journal. It has a lot of technical points, but at the same time, it explains this particular technique very nicely. Please take a look when you can. And the kind of source and detectors that is used, especially the instrumentation that Khushbu will show you later on. The photoconductive antenna, we call it PCA, photoconductive antenna. So this PCA technology is again wonderfully explained in this particular paper by Borford. So please take a look when you can. And these are just the schematics and the specifications of the setups that Diksha and Khushbu will be presenting later. I have just shown you the overall schematic. I'm not taking you through it because they will be anyway showing you with that. I'm just giving you some of the typical parameters and specifications of these two setups. And then quickly, I will show you some nice sort of results. These are just some results that I'm showing you. So this is actually the Raman spectroscopy of pigments. This is actually one typical flower that is very common in IIT Delhi. And so usually the summer students that comes, like the BTech students, or even sometimes school students, they come to work in the lab. And so to extract the pigment, they need to collect the petals, wash them, and then dry them, and then crush them. I mean, basically the sample preparation is actually a project in itself. And obviously some of the students, I mean, you remember Urbi, she's from a bio background, so she actually takes charge of all of us when all the people who are from the physics background or E background, we completely are out of depth, then she takes over saying that, okay, okay guys, this is how you do it, and things like that. But so once you make these sort of things, once you put them in the Raman, you can see very clearly that even a fresh leaf in a plant or even a pluck leaf, they also have carotenoids, the typical this yellow and orange color, the molecule, but the chemical, but because the leaves are green, we all know from our very childhood, it contains a high level of chlorophyll. On the other hand, the petal pigments, the pigments that was extracted from the petal, this yellow flower, you can see the comparative ratio of the carotenoids are much higher over there, while the chlorophyll is slightly low. Now I'm over here, I'm showing you actually a pizza base. So you can see that this pizza base is in its, the usual plastic sleeve. And sometimes what happens, because India is a very humid country, temperate climate, so these pizza bases, they do develop fungal infection, basically yeast infection. And even through the plastic, with the naked eye, it is very hard to guess that, okay, this thing has gone stale, or actually has got fungal infection. But when you put it under terahertz, what it does, just because a fresh pizza is slightly actually on the drier side, I will say, because as the fungal infections starts to grow, they accumulate more water near around them wherever they are colonizing the pizza, so to speak. And so you can see this sort of the stark difference in the fractal volume of the water. So these are actually water features. You can think of it like this. So this blue part is just the base, the flower base. By this red things are actually these small holes that are actually in the pizza base. But whenever the yeast infections are forming, they tend to form near around these holes, and they tend to collect more waters near around them. So just showing you what are the possibilities. So now I will actually okay. I need to. Okay, now I will go to the Raman spectroscopy demo given by Diksha.
So this is a home-built Raman spectroscopy setup. It consists a laser light which emits at 532 nanometer. Power of the laser can be adjusted up to 250 milliwatt. This is the periscope. It is used to adjust the height of the laser beam. Since the height of this laser and the height of the slits is different, so to adjust that, we can use the periscope. This is the beam expander. After passing through from the periscope, the laser passes through the beam expander. It changes or it increases the diameter of the laser beam. Then after passing through these mirrors, the laser light falls on the prism. This is a holographic laser bandpass filter. It removes the unwanted wavelength from the laser line and passes over 90% of the laser line. After this, the light passes through this microscope objective. It provides a 20x magnification and with 30 millimeter working distance. This is the sampler positioner. It can move in X, Y, and Z direction. Here, it is used to focus the light laser beam on the sample. The focus light excites the molecule in the sample and produce scattering, inelastic scattering. That scattering light included both Stokes, anti-Stokes, and Rayleigh line. This is the confocal arrangement which removes the out of focus light from the scattering which is coming from the sample. This one is the notch filter. which removes the highly intense relay line from the inelastic scattering. This is the entrance. From here, the laser inserts in this spectrometer. This diagram is showing the inside view of this spectrometer. Light enter from this one. There is a mirror which is this, and then there is another mirror. So the light passes through these mirrors, and then this is a triple grating which is actually inside this spectrometer. So the scattered light dispersed from this grating. There are 3 gratings, 600, 1200 and 1800 lines per millimeter. Then this light is recorded by this CCD detector. This is the camera which is used if we want to locate a particular position inside a sample. So with the help of this camera, we can find out that location and record the Raman spectra from that particular region. Now I will check the spectra of commonly used food additives. So this is sorbic acid, which is used as a preservative in many food compounds. This is the spectra of sorbic acid. As you can see, there are many peaks of the sample. This peak corresponds to the functional group of the sample. From here, we can change the frequency wavelength range, and from here we can choose any grating. These peaks are specific to the sample since this corresponds to the functional group of the sample. So due to this, the Raman has several applications in food science. It can be used to identify different components of the food such as protein, fat and carbohydrates. It can be used to identify any food adulteration in any food product, or to characterize the pigments and to find any dyes and microorganisms. So this is another food additive which is MSG, monosodium glutamate. It is a flavor enhancer. This is the spectra of monosodium glutamate. As you can see, there are no sharp peaks as like sorbic acid, but this is showing that there is some peak. In this case, we can accumulate data for few averages. So here I will record it for 20 accumulations. So this accumulation will increase the SNR and this peak will be more clear. So from here I have started the recording this data. So already this 6 accumulations are done. So as now you can see, this peak is now more clear, and also we can see few more peaks. So if the peaks are not so clear, so we can accumulate this data for few averages. Also we can increase the exposure time. If the peaks are not clear, we can do few adjustments to increase the SNR and so that the peak can become more observable. The Raman spectroscopy has a great potential to check the health of a plant. So here I will perform a quick experiment. This is a mango leaf. This is freshly plucked. So first I will record the spectra of this leaf. Then I will keep it in the dark for 15 minutes and then again take the Raman spectra from the same spot. This is the spectra of freshly plucked leaf. These peaks are corresponding to the carotenoid, and this is for the chlorophyll. Now I will save this spectra. So I am saving it, and then I will again record it after 15 minutes. I will keep the sample in the dark for the next 15 minutes, and then again we will record the spectra from the same region. And now I am keeping this box over the sample so that it can be in full dark for the next 15 minutes. We will take the spectra, another spectra after 15 minutes. So again we will take the spectra of this one. So laser is passing from the same spot, from the same region. So as you can see, this intensity of these peaks, this one, the chlorophyll has reduced now. So I will save this spectra also so that we can compare these. So now I have saved it, and again I will open the previous file. so that we can compare these. Is after 15 minutes. This is the freshly plugged data. So you can see that intensity has significantly dropped when it was under stress. Therefore, this Raman study suggests that it's a good tool to measure if the plant is healthy or not. It is under stress, or if there is some changes due to some environmental factors in the plant. So that can also be studied with the help of Raman spectroscopy. So now the Khushbu will tell you about terahertz spectroscopy. Thank you.
Thank you so much, Diksha. So this white box is the main unit of the pulsed terahertz system we have in our lab. It is TeraFlash Pro from Toptica Photonics. So this white box consists of a femtosecond laser that is centered at 1560 nanometer. The pulse width of this femtosecond laser pulse is around 60 femtosecond with a repetition rate of 100 megahertz. Along with the femtosecond laser, there are two delay stages. One is the mechanical delay stage, which is used to compensate if there is any path difference of the terahertz radiation. And this mechanical delay is the long delay. The other delay is electronic delay, which is based on voice coil and digital position sensor. This uh, electronic delay is required for sampling of terahertz radiation using the femtosecond laser pulse. So what happens inside this white box is the femtosecond laser pulse produced at this laser is divided into two parts. One goes to the emitter and the other goes to the detector. These blue cables are dispersion compensation fibers which are used for the propagation of femtosecond laser pulse to the emitter and to the receiver. The gray cable is to provide bias voltage to the emitter, and this black cable, this brings the output from the detector to this white box again. So as our system is photoconductive antenna based system, we need two photoconductive antenna, one at the emitter side and one at the receiver side. This is the receiver antenna and this is the transmitter antenna. This black cylindrical housing contains the photoconductive antenna and the silicon lens, which is used to reduce the divergence angle of the terahertz radiation generated at the PCA. And a pair of off-axis parabolic mirror is used at the emitter side to guide and focus the terahertz radiation onto the sample. Similarly, at the receiver side, this encasing contains the receiving antenna, receiving photoconductive antenna and the silicon lens. And again, there is a pair of off-axis parabolic mirror, and with the help of these two off-axis parabolic mirrors, the terahertz radiation after interacting with the sample goes to the detector. The average power of the terahertz radiation generated in our system goes up to 50 microwatt with a pulse width of 0.6 picosecond, and the peak dynamic range of the signal goes up to 90 dB for an average of 1000 and more. This system can be operated in both transmission and reflection mode by changing the alignment pin. Right now, we have kept the system in reflection mode. So the first window shows the terahertz time domain pulse that has been reflected from the metal, and the second window shows the A50 of the same terahertz time domain pulse. So right now you can see the terahertz time domain pulse as well as the A50. It's not stable, but it keeps on fluctuating. This is because we have taken two averages, and what the VCA does, as already explained, that it is required for sampling of the terahertz radiation. So every time it takes two average, like it samples 2 terahertz pulse and refreshes it. Unlike Raman or FTIR spectroscopy, terahertz spectroscopy is sensitive to molecular structure, and it exhibits low frequency rotational and vibrational modes of different molecules, different classes of molecules. So in this experiment, what we are doing, we are taking 3 samples. One is Teflon, the other one is sucrose, and the third is lactose. So Teflon is known for its transparency in terahertz range, whereas sucrose and lactose are saccharides. Sucrose is monosaccharide and lactose is disaccharide, and both these molecules have fingerprint in terahertz range. So this particular experiment is performed in true reflectivity mode. That means we have not placed metal plate under the sample. So since we have only one set of emitter and detector, we are raster scanning the sample point by point and line by line to generate the entire image. So this image clearly shows the 3 pellets that we have kept here. The first, this is for Teflon, this one is for sucrose, and this one is for lactose. And you can see the difference in the color, which represents the difference in reflectivity of the samples. And the sample holder itself, it is in blue color. So blue represents minimum reflectivity, whereas red represents maximum reflectivity. So from this image, we can conclude that sucrose has the maximum reflectivity, hence it appears in red color, whereas Teflon and lactose, which are relatively transparent, appears in orange and yellow color. In the second experiment, we are imaging 2 different leaves using broadband terahertz setup. So these 2 leaves are different in terms of venation pattern and their characteristic and the initial water content. And looking at the image, you can clearly see the venation pattern of the second leaf is clearly visible, as there is low water content compared to the first leaf, and whereas in the first leaf the venation pattern is not clearly visible, but you can see some subsurface infection which cannot be seen by naked eyes. One should remember that these images are pattern of the second leaf is clearly visible, as there is low water content compared to the first leaf, and whereas in the first leaf the venation pattern is not clearly visible, but you can see some subsurface infection which cannot be seen by naked eyes. One should remember that these images are maximum intensity time domain images and can be converted to frequency domain. Since we have broadband terahertz setup, we can get images at different frequency. Thank you so much for your attention.
Sorry. Okay. So by the way, both Khushbu and Diksha, they are here. If you have any questions when the question and answer session will open up, you can also ask them. Urbi is also there, who actually guides us for the sample preparation. So any question regarding the sample preparation can also be answered by Urbi. So just I'm finishing. I'm just posing you a question. Can photonics help? Because I'm showing you a very pleasant person from Kulu. It's a great place for tourists also. It is in Himachal Pradesh, North India. But because of the climatic changes, rising temperature, they are forced to shift from their very traditional farming product, which was apple. They are actually the apple basket of India, Himachal Pradesh. They are now forced to do more and more vegetable production. On the right-hand side, I'm also showing the typical urban Montreal in Canada. And in fact, this particular warehouse, actually at the top of this warehouse, they have set this amazing greenhouse to grow eggplants and tomatoes to meet the demand of the local demand for locally sourced food. And in fact, this is, I got this from the Wikipedia, and they are the largest greenhouse in the world currently. So if you have any questions, suggestion, discussion, or any collaboration option, you can just simply drop an email at loveofconcept@gmail.com. So thanks. So with that, I will stop sharing. Yeah. Thank you. So over to Pramit. Is Pramit there? I think. I don't know.
I am there.
Oh, okay.
Thank you.
Yeah.
Thank you.
Thanks.
Just a moment. Let me share my screen. Hold on.
Okay, let us know if you are encountering any difficulties. I haven't seen your screen yet. Pramet, are you still there? Okay, seems like maybe he's gotten disconnected, so we'll send him a message and hopefully reconnect. Parajita, if you're able to please follow up directly with Pramet.
Okay, let me call. Let me give him a call if he's experiencing some issues.
Okay, so he's just left the call. I assume he'll reconnect and share. Maybe, Parajita, if you don't mind, we can take some questions right now in the meantime.
Yeah, sure. Would love to.
Okay, so we'll see if anyone would like to put something in the chat. Your videos were beautiful. These are fantastic lab tours. It was very nice to see.
Okay.
It's all the
Just so one thing. Yeah, I called Pramit and he just got logged out, so he's just logging back in.
Perfect. Okay.
Yeah, and it's actually all students. So I mean, they are wonderful in the lab, and they are the scientists. So it's all kudos to them. Okay, I think Pramit has logged back in.
So we have a
Yes.
question. Oh, it's Pramit's here. Okay, we'll hold the questions to the end. Thank you, Joshua. Go ahead, Pramit.
Okay. Okay. Hold on. Try my level best to get my stuff up.
Yep, that looks like it's working. It's starting sharing screen.
There you go.
Yeah. Yep, there it is. Perfect. Thank you.
Okay. All of you can hear me, I guess, right?
Yes, we can.
Okay, great. So thanks to the organizers, especially Amartyo and Aparajita, for allowing me to share some of my thoughts out here. Now, what I'm going to talk about is something we do regularly in a lab, the technique, fluorescence, about its basics and applications. Followed by this, we'll be having demo of fluorescence with regards to the topic of this conference, the symposium. So with regards to this, can you see, are you still having this top button out there? Can you see the full screen?
The screen looks good.
We can see the full screen from it. Go ahead.
Okay, great. So this is the basic diagram, the Jablonski diagram that one uses when describing or teaching fluorescence. So what you see out here are different energy levels. So without going into too much details, what you have is you have the ground state, the ground singlet state as 0. Then this compound or molecule absorbs a photon or photons, then it goes to different excited states. So what happens is that once, say, it comes down to the excited singlet state, first one, S1. So from there, if it returns back to S0 by emitting photons, okay, so let me just change the color of my pointer. So if it comes back by emitting photons, as written as, then the process is referred to as fluorescence, okay? So this is the process I'm talking about. Now, how much of the photons or how much of fluorescence you'll be having will depend upon the competing pathways, which are the non-radiative ones, like internal conversion, then intersystem crossing. And intersystem crossing, what it does is it allows your system to cross, to have a spin flip. That means from the singlet, it goes to the triplet. And again, from the triplet also, you can relax down to the ground singlet state by emitting another set of photons. And that process is referred to as phosphorescence. So this should give you an idea that intersystem crossing, with regards to the fact, is a spin forbidden transition. Hence, phosphorescence is a delayed process as compared to fluorescence. So first you'll be having fluorescence, and then you'll be having phosphorescence. Now you can modulate both fluorescence and phosphorescence with respect to certain characteristics of their molecule. Okay, so what are the de-excitation pathways? So one is the radiative de-excitation that we just looked at, fluorescence and phosphorescence. Radiative means you're giving out photons, and the other one is the non-radiative de-excitation pathways, which are vibration relaxation, internal conversion, intersystem crossing, and so on. Now, this is a very important parameter in fluorescence, which is the quantum yield. So it tells you how intense, how probable your fluorescence is. So the expression for this quantum yield is very simple. It is the number of photons emitted over the number of photons absorbed, which means that you have 100 photons absorbed, and if all the 100 photons absorbed are emitted, then you have a quantum yield of 1, right? So there are dyes which have very high quantum yields, but there are also many fluorophores which have very low quantum yields. Then what are the typical factors that affect fluorescence? As listed out here, they can vary from something like the rigidity of the structure. So if it is not too fluctual, not too flexible, if it's very rigid, then what is going to happen is that the rotational, this interference will be low within the molecule, hence so your quantum yield will be higher. Then you have temperature. So higher temperature typically leads to lower fluorescence because of enhanced deactivating collisions. Then you have solvent effects. Then you have dissolved oxygen, which acts as a quencher. Then your compound can be pH dependent. So that will also bring about a modulation in your fluorescence and obviously the concentration. So this is the typical fluorophore. So you can see the fluorophore to the right of the screen. And what you're seeing here in this panel, if you follow my pointer, is the fluorescence spectrum of this molecule in different solvents. For example, H is hexane, CH is cyclohexane, T is toluene, E is ethyl acetate, B is butanol. And as you see, you're increasing the polarity of the solvents from left to right. What is happening is the color is also changing from hexane to butanol. So this is typically how fluorescence manifests itself. This was an example of where the solvent or the environment, right, dictates how the fluorescence would be. Now, this shows the fluorescence of an amino acid tryptophan. So yesterday there was a very good talk on proteins and network in plants or with respect to plant-related proteins. So many proteins will be having, amongst many other amino acids, this amino acid tryptophan. So now why did I single out tryptophan? Because not only because of the fact that I'm going to use that as one of our demo systems, right? When we give the presentation, the live one, live in the sense recorded one. This tryptophan is an intrinsic fluorophore. So it's one of the intrinsic fluorophores. There are 3 intrinsic fluorophores: tryptophan, tyrosine, and phenylalanine. So the one we end up using the most, like for people working with proteins, is tryptophan. So why is that the case? Because tryptophan amongst these 3 fluorophores has the highest quantum yield. And also this tryptophan is very environment sensitive, right? It's easy to get its emission because its quantum yield is higher with respect to the others. Now, when I say, what do I mean by this tryptophan, being sensitive to the environment? So if I just go to the next slide, and if I can, bring your attention to the first one. So this is the protein. And what you see, the red one is your tryptophan. So if you go from 1, 2, 3 to 4, what you typically are seeing is that the tryptophan in 1 is very buried. That means it's in the core of the protein. Then as you move to 4, the tryptophan gets more and more exposed, right? Exposed means it gets exposed to the surrounding solvent molecules, because that's where proteins are mostly studied. As a result, what happens is, now if you come back here, this is what it shows, that this tryptophan is the core and this 4 is exposed. So according to this variation in the location of the tryptophan in the protein, its fluorescence spectrum intensity and where the emission of the tryptophan comes will also vary. So using that, you can make some initial judgments, right, about what is the protein like, what is the structure like, whether the protein is folded, whether the protein is unfolded, and so on. Now, why did I take this tryptophan again? So the other reason is that, though I'll not be showing that here, that many, studies like looking at the freshness of samples, like fish samples, even meat samples, they have looked at this emission of tryptophan, obviously using fluorescence, and using that emission of tryptophan or the variation of the same, they have been able to predict whether this sample is fresh or how old is the sample is. Okay, so this is an example of a compound curcumin. Now, curcumin is a major ingredient of this popular spice in India. It's turmeric. So curcumin being the major compound, it's about, I think about 70 to 75% it's out there. So this is the structure of curcumin. This spice or this compound, which is a part of the spice, turmeric, also has its own fluorescence, right? So in other words, if you want to detect curcumin, you can actually use its fluorescence, its intrinsic fluorescence too. Now, why did I take curcumin? Not only because of this, that it's part of a well-known spice, but because curcumin has many medical benefits, many medical benefits, anti-cancer, anti-tumor, and so on. It even has anti-aggregation effects, some of which we have studied in our lab. Now, there is another application. So this is where we are looking at the emission of chlorophyll. So this goes back to one of the things that was shown using Raman spectrum of chlorophyll. So here what you're doing is you're looking at a leaf. So if you look at A, so this gives you a homogeneous fluorescence image of chlorophyll on a full leaf, right? So you're doing a fluorescence imaging of a leaf out here. Now, what does B do? In B, what has happened is the authors have taken this leaf and have subjected this leaf to a certain compound, which is an inhibitor of the photosystem to electron transport. As a result, what has happened is when you come from A to B, which is after 2 hours of subjecting this leaf to this inhibitor, then immediately you can see that the fluorescence has become inhomogeneous. So again, using fluorescence or using the fluorescence of chlorophyll, you will be able to look at the status of a leaf and then make other judgments based on that. Even the nitrogen content, as people have shown, can be looked at or can be quantitatively assessed using the chlorophyll fluorescence. Again, another one using chlorophyll is here. What you are seeing is that this is the chlorophyll fluorescence emission. Now, depending upon where you're looking at, whether you're looking at a part of the leaf, which is the palisade parenchyma, where you have extensive amount of chlorophyll, a high concentration of chlorophyll, or the spongy parenchyma, where you have a low concentration of chlorophyll, the corresponding detected chlorophyll spectrum or intensity would be different. And why is that so? Because if you look at this red one, which I said is the emission, this emission of chlorophyll also overlaps significantly with the absorption of chlorophyll, which is this black one, which means that if I'm having emission coming out and if this absorption band is overlapping with the emission band, then it's going to reabsorb some of the emitting photons. So obviously, where will it reabsorb the most? It will reabsorb the most out there where the concentration is very high. That is why the palisade parenchyma, where there is a very high concentration of chlorophyll, gives a lower intensity than that of the spongy parenchyma, where the chlorophyll concentration is low. Okay, so moving on from chlorophyll, let's look at another application of fluorescence. So this is looking at cod fish samples, which have been processed at different temperatures. So you can see these temperatures like 50, 70, then the raw fish and so on. So they're trying to monitor the fish sample being processed, okay, as a function of temperature. And what you're looking at hyperspectral fluorescence imaging. So in the hyperspectral fluorescence mode has not been used that much. So hyperspectrum itself is a different kind of spectra. It gives much more information, it's much higher resolution. That's what hyperspectrum tells you. But anyway, coming back to this, the hyperspectral fluorescence mode tells you or gives you information about the status or the cod fish sample, the status of that, or the quality of that. Now, this is a very interesting use of fluorescence. So what you're seeing out here is you're seeing the spectrum or the fluorescence spectra of tissues of spinal cord, brain, kidney, right, and many others of cows. Now, why was this done? So before I tell you that, if you look at this solid one and this dotted one, so these are tissues from the central nervous system. So this end up having the highest emission intensity as compared to the same one coming from the other tissues, which means that if your meat, say beef, is contaminated with CNS, that means the central nervous system tissues, then using fluorescence as a marker, you will be able to figure out and then discard that or take remedial measures. Now, why is this important? Because all of you have heard of the mad cow disease. It is a very fatal one. Now, the way it kind of gets inside us is if you are going to have meat which is contaminated with these CNS or central nervous system tissues. So that's why the fluorescence is being used as a marker to see whether you have that tissue as a contaminant on your meat. So in the same way, you can also identify milk using fluorescence. So what you see out here is the fluorescence spectrum of the milk, right, coming from different samples. So when I mean different samples, what is that? So it is coming from, say, if you look at the color code, so one of the, or one set of cows has been provided with a grass-rich ration. Another one, say, with a regular ration, right, straws and all. And this is riboflavin. So riboflavin, so if you look at these spectra, the milk fluorescence, this is what your milk fluorescence is, which contains riboflavin that, contributes to a huge extent. But that is not the actual thing. How do you detect? So you're going to use this to detect whether the milk is coming from cattle having this kind of ration. So if you would do a different spectrum, that means if you would subtract the spectrum of riboflavin out from here, what you would see is that here you have this spectrum. Now this spectrum is coming from a metabolite after metabolism of chlorophyll, right? And this is corresponding to this compound, thiophorvite A. So what you typically see out here is that wherever you have the grass-rich ration, right, there, this one stands out. So which means that if you take a milk and if you just take a fluorescence spectrum of the same, run the difference spectrum, you will be able to tell with a certain degree of certainty where from this milk has been taken or what type of ration the corresponding cattle has been fed with. Then this is another very interesting application of fluorescence. So this, again, is a contamination issue, but this is about fecal contamination. Now, I'm closely related to this because when I was doing my PhD in, Petrich's lab, Jake Petrich's lab, this is at Iowa State. So I was involved in some of these measurements. So what was the goal? The goal was that if I have fecal contamination in meat, can I use fluorescence to figure out the same? So what you see out here is, especially look at this one. So this is the metabolite coming from chlorophyll, right? And if the same, that means the feces is on your meat, right? Then you should be able to detect the same. So what we did was we analyzed a lot of fecal samples, right? It does not sound so interesting, but we actually had to do, and we did find huge amounts of variation depending upon, again, the types of ration these cattle were fed. So again, zooming into the same one, what are you comparing out here? You're comparing, if you look at the solid line, this is just meat, pure beef meat, okay? Then this one is the same sample contaminated with fecal stuff, and this dotted line is the actual spectrum of your feces. So looking at this portion, you'll be able to figure out how clean your meat is. And if it's not clean, again, then you take remedial measures. Right. So that was about the applications of steady state fluorescence. So I'll quickly go through time resolved fluorescence because that is also a part of our demonstration. So in time resolved fluorescence, that it says that we have a sense of time. That means we want to know how long, once excited, the fluorophore can stay in the excited state before it comes back or relaxes to the ground state. Okay. So this is, again, the same picture. I'll skip this. So it is typically first order kinetics, and then this fluorescence lifetime is related to this rate constants. So what happens okay, without going into the specifics a lot, is that I have an exciting pulse. That means I excite my sample, right? The sample absorbs the photons from the pulsed laser. It goes to the excited state. Then it emits photons. It starts coming down to the ground state, and we look at this decay. Now, why do we need lifetimes? Obviously, it has its own utility. So it gives an absolute measurement. Why? Because, you know, when you do a steady state fluorescence, you're always worried about the concentration from a sample to sample variation, right? So suppose you're doing a quantitative assessment, you got to make sure that once you take sample 1 and you go to the same sample but a different batch, sample 2, then if you're going to compare anything, you make sure that the concentration is the same. Errors can come in. But for lifetime, in almost majority of the cases, you do not have that problem. Then the lifetime again is a very sensitive probe of the local environment, which fluorescence anyway is. It adds an additional dimension, so you can do fluorescence lifetime imaging, like even using chlorophyll, you can do a fluorescence lifetime imaging and look at the heterogeneity of your sample. Then you can look at dynamic versus static quenching. So this quenching is very important for your photosystem too, because, you know, chlorophyll, if I can make the point, chlorophyll as such is not that fluorescent. Why is it not that fluorescent? Because of that electron transfer cascade that exists in photosystem too. It very quickly deactivates. That means its fluorescence is lost very quickly. So that's why it's not that fluorescent. However, if you manage to perturb the photosystem to electron transfer, then the quantum yield starts increasing. Then obviously there are other applications like cellular imaging that people have used extensively. And in biomolecules, what you end up using is the FRET. Okay, this is a schematic. I'll not go through this in details because I'll be having it in the demo. So you have a pulsed source, and then you have a sample out here, right? This is your detector, and then you correspondingly get a emission decay. So what is something that I want you to notice or take note of is that you have a laser pulse out here. So this is called the start-stop measurement. So that means how do you invoke this concept of time in this time-resolved fluorescence? So what you do is you have a laser pulse. So when the laser pulse comes in and hits the sample, at the same time, the laser pulse also triggers a clock, right? So now what happens is when the sample emits a photon, this photon then comes back, and what it does, it stops the clock running. So that timing, you know, from its initiation or its triggering by the laser pulse to getting stopped by detection of the photon is that time which is getting registered, and that's how you get your lifetime. So you essentially end up getting a histogram. So this is typically how the fluorescence decay looks. So this is of a compound anthracene in cyclohexane. You see, this is the blue one is IRF or LAMP. So IRF is what? It's an instrument response function. You need to know how fast your instrument is behaving. And also you need to have this IRF if you would want to fit this decay, right, to get your parameters. That means you get your lifetime to exponential functions. It can be single, it can be double, or so on. So here I end my presentation. So what I will now do is I'll move on to the demo. And let's see whether I can start it. Can this be seen by everybody?
Yes, Pramit.
Yep, we can see it.
Yeah.
Great. So hold on, let me see where I can start. Tell me whether you can also hear it. I just want to.
The volume is a little low.
The volume is a little low, so let me try to increase it.
It might be a few. Oh yeah, maybe that'll work. That's great.
Hello, everybody. Welcome to our lab. How about now? Is it okay?
Oh, yeah, I think it's okay. It's better.
Great.
Thank you.
So what I'm doing right now is I'm standing in front of fluorometer. So this is a steady state fluorometer. The first set of experiments, we are going to use this instrument to demonstrate some of the things that we have discussed just before through the slides. So let me walk you through the instrument. So what we have is, this is our lamp jacket where the lamp is housed. So this is a xenon lamp. Its power is 450 watts. Now this lamp, what it does is it delivers the flux of photons through this portion into the first chamber. Now this chamber houses our excitation monochromator. From there on, the same light is focused onto
the sample holder. So this is our sample chamber. So as you will soon see that my co-worker Harshita will be demonstrating how to put the sample inside. Now, if you would also notice that when I come from here, which is the excitation part, that is having the excitation monochromator, to the sample chamber. So I'm coming through this geometry. Then on this side, I'll talk about this later, but on this side, if you look at this portion, this is the emission side. So this is the box which houses the emission monochromator. Again, going back to the geometry, if you see I'm coming like this, this is where my sample is, and then I'm going like this. So this is the typical 90-degree geometry that we use when we do our fluorescence experiments. Okay. Now after that, what happens is, if you would see out here, this black box kind of thing. So this is, as I said, was our emission part. So from here, after the monochromator, the light is focused onto the detector. So this part was about the instrumentation. So one thing I missed, I said that I will come back to later, is this portion of this accessory. This is called multi-well plate reader. So that means if you have many samples together, suppose you're doing say 48 samples, 96 samples, okay, 384 samples, then I can put in plates inside. The same instrument being an accessory can be coupled to this light source, that is this instrument, and I can do a high throughput assay. High throughput assay means high means many, throughput means I'm assaying many samples together at the same time. So that's why it's called a high throughput assay assembly or multi-well plate assembly. This unfortunately will not be using today. However, all the basic parts of the spectrometer will be coming into play, as I discussed, when we actually do the samples. So now what I'll do is I'll hand it over to my co-worker Harshita, and she will start actually giving a demonstration. I will be around and I will explain as she does the process and for what she's doing, the reasons behind the scene. Okay, so then let us start with the demonstration. So the fourth sample, Harshita, she is putting in. So Harshita, just for information, is doing her PhD in our group. So she has put in a sample, which is the sample BSA. So BSA is what? It's a protein. It's the full form is bovine serum albumin. That is, this serum protein is derived from cows. Okay. Now, as you would remember our discussion, so this protein will be having some intrinsic fluorophores, and the fluorophore that she is going to focus on is tryptophan. This protein BSA has actually 2 tryptophans. So what she is going to do now is she is going to show you how to acquire the spectrum of tryptophan in this protein BSA. Okay, so let us start with the experiment, as Harshita is going to show you. Now she is going to go to the next step. So she clicks on emission scan. So now she is going to set the scan range. Okay, so let's go and collect it. So here you can see the spectrum being recorded. So on the x-axis, we have the wavelength in nanometers. So remember the range we have. On the y-axis, we have the counts. So this is how the emission spectrum is developing. It started from a low value, then it goes to a high value. You see that the curve, the emission spectrum is typically curved at the top. There is a maximum. This maximum is the one which we refer to as the emission maximum. And this emission maximum for tryptophan will depend upon which protein it is a part of or which solvent it has been taken in. So let's go ahead and see how the emission spectrum is getting collected. You can see now the spectrum is going down. That means the counts are going down. It will come to close to 0. But since we have set the range to 560, so what it will do is it will go all the way to 550, and then the spectrum collection will be stopped. So as you can see now, the photons are being collected, or the detector is collecting counts close to 450 nanometers. So now what Harshita is doing is that she is taking a cursor and she is trying to tell you where the emission maximum is. So the emission maximum, you can see the bottom where she is having her cursor. It is at 342 nanometers. Now, Harshita, can you expand this window? Yes. So now if you see the right hand portion in yellow, there you can see what the conditions she has kept. Excitation is at 295 nanometers. Then we started the emission around 305 nanometers. We are going to stop it at 560, or I guess it's 580, right? Then the step size is 1 nanometer. That means it is collecting at 1 nanometer intervals. The dwell time we discussed is 0.5 seconds, right? The repetitions is 1. That means you're only going to collect 1 spectrum. Then we have the excitation BW. BW means bandwidth. 2 means 2 nanometers. Emission bandwidth is 2 nanometers, right? The others we don't worry about right now because those are just specific details. So as we can see, the emission spectrum collection is almost nearing its completion. So this is typically how the tryptophan emission of BSA looks. And just to remind you that BSA has 2 tryptophans. Okay. So now we are done with the collection of our first sample spectrum. So now Harshita is taking this sample out and she is going to put the next sample in. So as you can see, she puts the next sample in. Okay, so let me tell you something about the next sample before Harshita changes the parameters. So now the next sample is the same BSA, but we have done a small change on it. So what we have done is we have taken BSA and one of its cysteine residues, right, which is an amino acid residue, the cysteine residues is now labeled with a fluorophore. This fluorophore we call an extrinsic fluorophore, as opposed to tryptophan being an intrinsic fluorophore. What do we mean by an intrinsic fluorophore? Intrinsic fluorophore is something which is already present in the protein, like tryptophan we saw the last time, or it could have been tyrosine or phenylalanine. Now what we're doing is we're actually adding a fluorophore from outside. How did we do that? So what was done was that the cysteine residue of BSA, which is the free cysteine, it was labeled with a dye, which is the fluorophore. Okay, the fluorophore is a coumarin-based dye. We call it CPM. I can share with you the full form later, but just for the sake of discussion, let's consider it as CPM. Now, why do we do it? That's the next question. The reason we do it is, sometimes what happens is that I can have some proteins which might not be having any tryptophan. Now, why am I saying tryptophan? Because tryptophan has a pretty high quantum yield as compared to tyrosine and phenylalanine. So that's why we always use tryptophans. It is very sensitive to polarity or changes in environment. That's why we take that. Okay. So suppose I do not have any tryptophans in a protein, then I'm at a disadvantageous position. So then what can I do? What I can do is I can see whether the protein has a cysteine residue or not. I can make that cysteine free if it is not already free, and then I can ligate a fluorophore to it. So this fluorophore, by definition being a fluorophore, will be having a high quantum yield. So what does it mean? What it means is that even if I do not have a tryptophan and I do not have much fluorescence coming out of it, right, because I do not have a tryptophan, but if I'm going to add an extrinsic dye, we call it an extrinsic label because we're adding it from outside or ligating it from outside, then what is going to happen is, then I'm going to realize, I'm going to see my protein now with this fluorophore. Now you're only going to look at the fluorescence of the CPM dye. So let's collect the spectrum of the CPM dye. Okay, the same drill as the emission spectrum was collected before. So again, if you can focus on the right side of the spectrum, all the scan parameters are given out there. You can see now excitation has changed to 390 nanometers. The start now is from 405, the stop is 600. Again, the step size we have not changed. The dwell time is about 0.5 seconds, the same thing. The repeats, that means only we'll be collecting only one spectrum. So the excitation bandwidth has been changed to 1 nanometer. It was 2 nanometer in the last spectrum. The emission bandwidth has been kept as it is. So here, as you will be able to observe now, that the emission maximum, if Harshita will be showing the cursor, yes, the emission maximum is at 468 nanometers. So remember, the emission maximum for tryptophan was 342 nanometers. For this one, it is 468. So different fluorophores, by definition, will be having their emission maxima at different places. That's why we have different fluorophores catering to different requirements or different experiments. Okay, so we're almost getting over with this one. So here the emission range is until 600. So once it reaches 600, it will stop collecting. So now Harshita is putting in the third sample of the lot. So this would be the last sample that we're going to do out here. So this sample is curcumin in ethanol. So curcumin is polyphenolic compound. And if you would know, this curcumin is very much available in an Indian spice called turmeric powder. So then let's collect the spectrum. Okay, immediately you can see a rise in the emission signal of the counts. So it means if you have curcumin in your sample and if you want to take a spectrum of the same, you're bound to get an emission coming from curcumin. But please also to keep in mind that curcumin happens to be an unstable compound, especially in water. So a lot of research has also gone in and is still going in, trying to stabilize curcumin so that it is made what we call is more bioavailable, that is increasing the bioavailability of curcumin. Harshita, can you just click on the cursor so that we can look at the emission maximum? right? So you can see the emission maximum is 537 nanometers. So now you think about the other fluorophores. So tryptophan had an emission maximum at 342, 340. The CPM dye had an emission maximum at about 468, 469. And the curcumin is having an emission maximum at about 537, 540. So 3 different fluorophores, right, having 3 different emission maxima, telling you that this fluorescent property is an intrinsic property, is a fundamental property of that species, of that molecule itself. Okay, so we are nearing completion, right? So we're done with the collection. So this is the emission spectrum of the spice curcumin. I should not say the spice, but curcumin is the major ingredient of that spice turmeric powder. And again, as normal to the right, you can see all the parameters that were kept for this collection.
How much time do I have left?
So we're actually
Out of time?
got an echo. Yes. Yes, we are.
Okay. So what I'll do is just can you give me just 3-4 minutes more? I'll skip the initial part and just show the data collection in the time resolved one. Just a moment.
Great. So now the laser is happy, the system is happy. Now we can acquire the decay. So you can see how the decay is being acquired.
So if I can just interject out here, this decay, your lifetime decay you're looking at is that of the CPM dye in BSA.
So on the x-axis, you have the time in nanoseconds, and on the y-axis, you have the counts. So the way the decays are counted is, if you look at the peak of the decay, so we say that the decay should be counted unless or up till that point that we have 10,000 counts at the peak. The peak is where she is having her cursor. So once the amplitude, that means the y-axis counts, reach 10,000, the decay will stop.
Okay, I will fast forward again.
Okay, so now we are going to acquire. So she optimized. Now you can see this red one is your instrument response function, and the blue one is your actual decay. So the instrument response function is much narrower than your actual decay. What does it mean? That the IRF or your instrument response is much faster than your actual lifetime, and hence you can reliably fit the lifetime decay. Okay,
so then I'll go to the last sample now. Okay, I'll start from here. So the last sample, the blue one you see is that the lifetime of curcumin, the same sample we did in the steady state spectrum. We echoed the steady state spectrum of. Okay, and the red one again is the IRF.
Blue curve, which is your actual decay. You see, this IRF is very almost very close to the sample. So that means the sample is decaying really fast. Okay, what does it mean? It means that the curcumin in ethanol has a very short lifetime. Okay, maybe in a few hundreds of picoseconds as compared to that of CPM, which has a long lifetime, a longest lifetime of about 3.5 to 4 nanoseconds. We'll end the demo session here, and it was just to show you how the data are collected, how the data is built up. After this, what we can do is we can take the IRF, we can take the corresponding decay, which is in blue, the IRF in red, right, and then fit using the fitting routine. And the fitting routine, what happens is you start with some guess parameters, then you vary the parameters and you try to get the lifetime. The lifetime of the fluorophores are typically in the order of nanoseconds. It can be a few hundred picoseconds, or it can be also very long, like 100 nanoseconds. Okay, it depends upon the fluorophore. So that will end.
So I'm done. Okay, I'll stop here, and I'll also stop sharing. Thanks again, and please feel free to ask any questions you have.
Fantastic. Thank you, Pramit.
Yep,
thanks. Very nice presentation and very nice lab tour and explanation videos as well.
Thanks.
So We have about 5 minutes left in the session, so a perfect time for some questions. And we did actually have one from following Aparajita's talk from earlier on, from Jayshree. You can unmute, or if it's been a while, I also copied the question and can ask. And I believe that the students will be answering the questions directly, so we're lucky for this opportunity to learn from them.
And I will also ask Diksha and Khushbu to switch on their mic and their camera so that they can be visible. They are actually sitting just beside me over here.
I think they just answered my question on the chat, but I guess my question, a follow-up on that was on the terahertz, what is the depth over which you're actually getting that spectral data? Like, for example, if you do a leaf, you're getting that sort of not the spectral data, sort of the intensity data over what depth? That's what I was looking for, if that makes sense.
Depth in terahertz.
Khushbu, you are muted.
No.
It's okay, we could hear you. You can go ahead.
Yeah, we are sitting together.
Yes.
Go ahead.
Use it in phone. Yeah. So in terahertz radiation, there is another parameter that plays role in the penetration depth. And as I showed in the second experiment, we were imaging 2 leaves. And in one of the leaves, you were able to see the venation pattern very clearly. The thickness of the leaf was around 1 to 1.2 millimeter. So definitely you can, it depends on the how absorbing is your sample. And depending on that, you can go up to, if your sample is less absorbing, you can go up to 2-3 millimeter in the lower terahertz region, like in the lower frequency range.
Okay, thank you.
Okay, thank you very much. If there's any more questions, please feel free to put them in the chat. Otherwise, I realize it is close to the end of the session. Oh, we have a nice comment in the chat. Says, I love the video demos, especially as I'm not overly familiar with the topic. Yes, these are very nicely done, a great way to learn more about it. So thank you very much for those, and thank you particularly to the students for doing those. I'll give another minute for there to be questions. In the meantime, I will say just a little bit about our final session that's happening in the evening in India or tomorrow morning in Canada. And so that'll be the high-level applications of new age science and technology. And we'll have a presentation by Dr. Bala Pasala, who is speaking on applied photonics and spectroscopy for sustainable energy and environment, and a talk by Dr. Mohammed Sabsabi, who'll be speaking about a look at laser-induced breakdown spectroscopy technique opportunities and challenges related to the agriculture field. And then we'll have an overview that I will give and going into a brainstorming session of ways that we can pull together the things that we've learned over the course of these 4 sessions towards addressing and tackling these grand challenges. So it looks like we're very nearly right on time to finish the session. I haven't seen any more questions come up in the chat. So we will thank all of our wonderful speakers for this evening or this morning. Very nice to see you all, and look forward to the discussions in the next section. So, thank you.
Thank you.
Thank you.
So Amina, maybe we can, Aparajita, and we can stay back for a while. The other participants could kindly leave, please.